Today we're looking at section 3.4, proofs with perpendicular lines. Our essential question, what conjectures can you make about perpendicular lines? First thing we're defining is a perpendicular bisector. So that is a line that intersects a line segment at its midpoint and at 90 degrees. So if we draw lines here, there we have meeting at 90 degrees. There I have it cut in half. Right. So if we're looking at these lines, AB is the perpendicular bisector of DC. Then we have the line linear pair perpendicular theorem, which says if two lines intersect to form a linear pair of congruent angles, then the lines are perpendicular. So linear pair we know is 180. So if 1 and 2 are equal, then they have to be 90 degrees. So if angle 1 is congruent to angle 2, then G is perpendicular to H, and our upside down capital T there is our symbol for perpendicular. So example 1, the diagram at the right, angles 1 and 2, or angle 1 is congruent to angle 2, what can you conclude about A and B? That's the theorem we just went over with, so my conclusion would be that A is perpendicular to B. Example 2, we're looking at solving problems. Okay. So 3x plus 6 and 90, they're vertical. So 3x plus 6 equals 90. 3x is equal to 84. And then x is 28. Okay. On B, these are 90. So these two have to be 90. So here 51 plus 2x minus 11 equals 90. So 2x plus 40 equals 90, 2x equals 50, and x is 25. Okay. We're dealing with 90 degrees. Generally, people don't find those problems hard, but think about what you're doing, because the setup can be different. Here, I have the one angle equal to 90. Here, they're adding up to 90. Okay. Then we have the perpendicular transversal theorem. It says if a transversal is perpendicular to one of two parallel lines, that it is perpendicular to the other. We could use corresponding angles or alternate interior or alternate exterior or consecutive interior, whatever we want it with this. Right? This is 90, so corresponding has to be 90. Alternate exterior has to be 90. So we could use that to show this. This is just another way of doing it. So if H is parallel to K and J is perpendicular to H, then J is perpendicular to K. And turning our page, lines perpendicular to a transversal theorem. This is the same way, just same theorem, just going in the opposite direction. So this is our converse. In a plane, if two lines are perpendicular to the same line, then they are parallel to each other. Okay? So if M is perpendicular to P and N is perpendicular to P, then M is parallel to N. And again, I could use like corresponding angles here. The advantage of this is that if the angles are in a weird position, we don't need to worry about it. But you can just use your other parallel, those four angles that go with parallel lines, corresponding, consecutive interior, alternate exterior. Example 3, determine which lines, if any, must be parallel in the diagram. Explain your reasoning. So now here I need to have them matching up. So for example, this and this are both 90 degrees. they share the transversal x. So based on 1 and 2 there, R has to be parallel to S. Okay. Then if I'm coming down this way, if I look at 1 and we'll call this 3, right? I have X and Y. X is parallel to Y. If we look at 2 and 4, X is parallel to Z. Okay, all of those are based on our lines perpendicular to a transversal theorem. For Y and Z, they are going to be parallel, but basically Y parallel to Z would be based on our transitive property, right? Which we haven't really stated out for parallel lines, but since Y is parallel to X and Z is parallel to X, Y and Z have to be parallel, but we don't actually have angles here that match up to show it. Then our next definition, distance from a point to a line. So it says the distance from a point to a line is the length of the perpendicular segment from the point to the line. This is fairly straightforward. I'm going to use a separate sheet of paper here to draw that out. If I have a line, my line, and I have a point not on that line, right? I can draw a bunch of lines from this point to these lines, right? So we want to be consistent in what we call the distance between them. So by definition, the line that hits at 90 degrees, that line is going to be our distance from the point to the line. It's also going to be the shortest distance, which makes sense. So that's what we want to use. So that's what this is saying. If we're looking at the distance from this point to this line, what we use is the line that hits at 90 degrees. So in example 5, it says find the distance from point A to line C. Okay? And round our answer to the nearest tenth. Okay? So I want the line that from A hits this at 90 degrees. We don't really go into this at this section. We go into this at a later point, which makes this a little confusing here. But if I look at the slope of this line, I come over 1, come up 1, 2, 3. If we flip that around, come down 1 and come over 1, 2, 3, that's the point where it's going to be 90 degrees. So this is the line that I'm looking at there. Okay. So then I need to find the length of that line. If it was horizontal or vertical, we could count. We don't have that. So we're going to use distance formula. Right? x2 minus x1 squared plus y2 minus y1 squared. So we have our point A. That's at 0, 2. And we have the point here, which we're going to call B, right, which is at 1, 2, 3, which is at 3, 1. Okay, so that's what we're going to be using as our points. So I have 0 minus 3 squared plus 2 minus 1 squared. So 3 squared is 9, 0 minus 3. The negative will cancel out. So positive 9. 2 minus 1 is 1. 1 squared is 1. So I have the square root of 10. All right. And if we take the square root of that, we get 3.16 to the nearest tenth. That would be 3.2. So that's how I find my distance. And most times that's going to be the case. You're going to use distance formula to find it, and you're going to flip the slope. So it's the reciprocal of the slope to find actually this negative reciprocal of the slope to find the line that hits that the perpendicular line. That is the end of 3-4.